All right. I think now's a good time to get started. So first things first, before I get into the main topic today, as always, consider becoming a Mr. Fourth member. Also, I just released on YouTube my new podcast with Abner Coinbray. We talked about Terminal Click. Terminal Click is cool because it's not a visual programming language, but it is a visual style thing. It is a graphical visual terminal. So just like how text files are a big, text-based interface for creating software, this thing here, this command line, very text-based interface as well. And Abner is working on graphical slash visual innovations in the terminal workflow space. So I talked to him about that and cross ideas together about visual control systems and stuff like that. Very cool. You can check that out on my YouTube channel. You can also find it if you go over to mrforth.com videos. There's the YouTube there. It's also a part of the podcast, so you'll find it on my podcast feed if you just want to listen to it on your audio player. And this also helps to fund the podcast work. So if you like the podcast and you want to support that part of what I'm doing, this is also the place to do that. All right. So for today, I am working on I have this list of projects here. The binary file and object file deep dive project is my focus today. And in particular, I'm going to be working on the COFF file format. This is the file format that the Windows operating system relies on for creating executable files. So all these programs, when we run them by loading up an executable file and turning it into a process. And this format also handles DLLs. So if you've ever seen the Handmade Hero hot reloading through DLLs, that's another type of PE file. And it also handles object files. So everything that comes out of the compiler and goes through the linker also relates to this format. So all these different file format or file types are mostly based on the same format here. And I am working on creating the very basic tools for comprehending this file format today. I have a little progress already, so let's take a look at what I've got. Let's see, we've got pedump.c is the dumper program. So I'll take you through that a little bit. Let me see what happens. What am I set up to build right now? I'm set up to build the dumper. Good. And what am I set up to run? Right. So let's focus on this one for now. I have 3 different test cases here for the dumper. So I should be able to build the dumper and then run it. And whoops, I want to see the run results. And we can see here after dumping the main or the test.exe from my build folder, we're getting all this info. So it's machine type AMD64. That means is that's just another way of saying x86-64. That's the Windows code for it. How many sections are going to be in this file, the timestamp, these are always zeros, some, header stuff, some flags. Then we get a bunch of this optional header stuff. All of this is optional header stuff. Data directories look like they're just like it says V off. I think that's wrong. I think that should be an F off. Let's go fix that. Right, because, well, let me double check. So here, where it says data directory, data directory, virtual address is actually the RVA of the table. The RVA is the address of the table relative to the base address of the image when the table is loaded. Okay. Okay, so this is claiming that it's a V off. So this is an important distinction that I'll probably have to explain a few times throughout this process. We have a file. It's an executable file. let's get HXD up here just to get us ready for this part. Mr. Forth build test exe, right? So we have this file here. Here it is in raw bytes. And if we take a look far enough down, we would find somewhere in here there's going to be the data for the data directories. Now, I don't know exactly where that's going to be. This looks like it could be section table stuff. So this could be data directories right here. Data directories are 8 bytes wide, so like maybe that's a data directory. I don't know for sure. There's the PE signature. So yeah, the header is probably somewhere in this range, with the sections beginning right about there. It's my guess. But the point is, the values encoded here are not giving us offsets into the file, right? This doesn't say file offset or anything like that. It says virtual address or RVA. And then it says the RVA is the address of the table relative to the base address of the image when the table is loaded. So you have to remember that what happens with these files, with executable files, is they exist as a file on the hard drive, like a normal file. And then when we run them as programs, when we turn them into a program, they get loaded. And when they get loaded, they do not just get copy-pasted exactly as they are. They get chunked up and put together in a new way. And so large sections of it might be copy-pasted, but they might be rearranged. There might be parts that get dropped. There might be parts that get moved closer together. And so when we talk about the virtual address, we're talking about the offset in the loaded space, not in the space in the file, but in the space after the data has been loaded in as a process. So there's basically two different forms the data has: the on file layout, and then there's the virtual space layout, right? And that virtual space layout, I call that a VOFF, like and the file space layout, I call that an FOFF, right? So virtual offset and a file offset. And it looks like the documentation says these are in fact virtual offsets. pe.h data directory VOFF. Yep, okay. So there we go. That's everything we've got so far. Is everything up to the data directories is getting dumped. So let's try to figure out what comes next after data directories and go from there. So the next up, it says there's a section table. Now, the position is required. Okay, so the section table is immediately after the optional header. So let's work on parsing this out. Here we parse out optional header. Parse the section table. Okay, so we have a structure down here already. Yeah, we do. So the section header has already been defined. So I grabbed this this here gave me the definition of the section header struct, which I have right here. So there's our section headers, and we'll have a section count. And so if the status of this is good, there must be after optional header offset. Great. So what we want to figure out is so here's the section headers off is the after optional header off, right? So this is the offset. And whenever I have off at the end like this, these are all file offsets. So I'm not actually writing that. Maybe I should be, but I'm not. But it says that the section table immediately follows the optional header. So wherever the optional header, wherever the byte is that starts after the optional header, that's the byte where the section headers begin. And then after section headers off is just that starting point plus the number of sections times the size of a section header, right? So there's our there's our calculations, except our section count is wrong. Section count, we're going to get that from... That must be living in one of the headers we already have. Is that in a COFF header? No. Yes, section count right there, right? Section count. So this is from COFF. COFF header cannot equal 0. Then COFF header section count. Little coffee break. Okay. So that's our section count. And what we want to do is we want to validate that this is going to fit inside of my input data. So I have this raw blob of data in a string 8 called the input data. Right, so I've loaded my file. I've stored it into this string 8. String 8 usually means a real string. Usually I'm using that for, ASCII or UTF-8 strings. But occasionally I also use it for just raw data blobs. So this is just a binary string, basically, a U8 block of data. And so after section headers off is less than or equal to input data size. And that means that the section table actually fits inside the file. So we're not going to just willy-nilly create pointers into the data that are going to create buffers or implied buffers that are not actually going to fit, right? We have a certain amount of actual data available. If we're going to say, hey, I've found a pointer here that points into that blob of data, and I'm giving it a length and a type. Like I'm giving it some kind of type that, tells us how big this pointer is. In this case, it's the type times the section count. Then that better actually all fit inside that data. Otherwise, I'm creating an array here that will not actually be valid, right? So before I create these arrays, I'm testing that they fit inside the blob of data. Input data string plus the section headers offset. That gives me my section headers. And if I can't get that, then we'll set good equals 0. All right, so good equals 0 means something bad happened. We can no longer continue making progress parsing. But if this works, then we should have a section header list now, and we can go dump that. So here we dumped the data directories. Section headers. Okay. And we have in my pe.h, do I have, yeah, the section table includes that. So now all that's left is section header. Let's begin a loop. So for I is less than the section count, I plus equals 1, pe section header, sec headers plus I, and then we're going to start printing these out. So what we have is section %u space I do kind of like that better now that I think about it. Let's change this one. So we have data directory %s equals, and that gives us directory name, and then space voff equals ox%x, new line size equals percent u, new line, close bracket. So we want directory name, directory voff, directory size. We'll do the same kind of layout here. Don't need separate prints for each one. Just a comma at the end. No paren there. Very good. Okay, so the section, let's see. This contains a name, which we can actually do using the old school method by just saying 8 and then sec name. So I goes there, section name is there, and the 8 is from the fact that this is a fixed size buffer, so it shouldn't be larger than 8. Comma, what else do we get? V size, percent $U, voff, ox%x, f size and f off, and then flags, and we'll put down a flag string there. All right, string 8, flag string equals, section flags, section flags, section flags. All right, now these aren't too hard to make. We just need to replace DLL flags with section flags and DLL flags here with section flags xlist. And then That goes away and gets replaced with that. Alright, so section flags has some duplicates. Let's take a look. Section flags. What's going wrong? So section flags. 1, 2, 4, 8, 1, 2, 4, 8, 1, 2, 4, 8, 1, 2, 4, 8, 1, 8, 2, 2. Okay. Let's take a look at what that's about. Why are there two of the same thing? Okay, well, they're both reserved for future use. So we might as well drop one of them since they mean nothing. And there's another problem here, which is this section here is not actually just a flag, is it? This is giving us a masked section. So this isn't quite going to work the way it did in other cases. How do I want to do this? I think those all need to go live somewhere else. They can't be a part of this X list. We're just going to delete everything here that says it's reserved. No point in actually having them. Link other. Reserved. Okay. Now this is masked section, right? What's actually happening here is that PE section, a line from section flags F is F and OXOOF OOOOO 4, 8, 16, 4, 8, 12, 16, 20. So there are 20 bits here that we want to shift away. And what we're left with is one of these. And so this is, if I subtract one here, and then I do a 1 shift on this. So this works if that's not a 0. Ah, this gets nasty. Let's not do it that way. Let's just do F and OXOO F 0 0 0 0 0 1 2 3 4 5 6 7 8. Good. PE section align. Okay, so there's our section align X list. And then we're going to need to go, okay, so when we're scanning along here, we're looking at each of these and adding them to the section flags list. And then we're also going to look and see what the alignment is. So this is the basic stuff, but what about the align? Section align from section flags. Bytes equals 0. Switch on. Well, this is just going to be section align. And then we're going to do define X, and this is going to be BC or ZC maybe. And in case we see a C, then we're going to straight list push arena out straight lit align and Z bytes. Right? It's like that. Undef X, PE, section align X list X. And stick that actually up here. Other flags. Okay. After optional header. After optional header off. Okay, flag string is going to come from this. We just worked on this function. So, let's just pull our scratch up a whole level here. Share it across this whole thing, make it easier. Scratch. Scratch. Okay, scratch arena. Grab those section flags. You put them in a string. And you dump it. Okay, so now we're going to need help from Remedy. All right, what did we miss? Directory name. Directory v off. There's a comma there. 327. Okay, that ran to completion. Let's take a look at the output. You know, we could play around with saying like, hey, these don't really need to be separate lines. Like, let's just go for a bit more of a compact look. Of course, now I wish these would all line up, and they don't. Oh well, I think I'm going to just let that be as it is. Maybe what I'll start doing, though, is, let's say we do at least want that extra new line after each big chunk, so that when we have a text file, we can do like jump to new lines to go between them. Type, COFF header, PE32 plus optional header, data directories, sections. Okay. So name equals .text, v size 126.1 kilobytes, v off, there's our v off there. 126.5 kilobytes total size of text, whereas this is 126.1 kilobytes. There must be more or something. These can't be right. These can't be right. So the first one is aligning correctly, but after that we're hitting some kind of a problem. Let's oh, you see the total size here must be the total size on file. All right, I'm going to pick up from here in a couple minutes. I'll take a quick break. All right. So this can't be right. Look, it's giving me lines for multiple spots. How is that even happening? Let's see. So I got two bugs here. One is that the sections get all borked after the first one. And the second bug is that the align flags don't even make logical sense. That shouldn't be possible for that to happen. Maybe I forgot to add a break statement is the answer to the second bug. Okay, so that got us the correct align. Now we want to track down how, probably it's a, yeah, someone in chat just pointed out. Probably there's a mistake in my section header type here. Let's see. Yeah, number of relocations, number of line numbers. These are both supposed to be U16s. So that will make the section header a little bit smaller. Two, 3, 4, 5, 6, 7, 8, 9. Okay. And that will mean that the stride would be different, and there we go. Now things line up. Here's me. Nice. Okay. And just for testing here, let's try out an object file as well. So with an object file, we don't get a PE32 or a PE32 plus, and we don't get data directories. So we go from COFF header straight into section table. And something interesting about the object files is they can't be loaded as images, right? So they don't have that virtual space. They only have an on-file space. And they can have duplicate sections because they're going to go through a linker, which is going to put all of these separate RData sections into a combined RData section. It also contains debug info. On Windows, the executables don't contain debug info because the debug info gets shuffled out to a PDB. But before the linker actually is responsible for the PDB generation. So before that, the compiler puts debug info into the object files. Okay. Okay. Now what do we want to do? So that's everything that we have, that I have prepared in my data structures. So after that, we're past the header stuff. The rest is different things we can find based on what section we're inside of, right? So why don't we read through some of this and come up with a plan for what to track down next. Some things that would be good to be able to do are, if I have a DLL, it'd be good to be able to see what functions are being exported from it. If I have like load time imports, it'd be good to see the list of that. Yeah, let's take a look. Section data. Initialized data for a section consists of simple blocks of bytes. However, for sections that contain all zeros, the section data need not be included. Sure. Data for each section is located at the file offset that was given by the pointer to raw data field. In an image file, the section data must be aligned on a boundary, as specified by file alignment field in the optional header. Section data must appear in order of the RVA values for the corresponding sections, as do the individual section headers in the section table. There are additional restrictions on image files if the section alignment value in the optional header is less than the page size of the architecture. For such files, the location of section data in the file must match its location in memory when the image is loaded, so that the physical offset for section data is the same as the RVA. That makes sense. So this is saying if you look at, like, remember we have two different spaces. We have a file space and we have a virtual space. So there's the way things are laid out inside the file, the way things are laid out once they are loaded. And it's not a copy paste. We're taking a subset of what's there and moving it over. We're also padding some zeros in some places. So there might be some places where we grab a section out of the file, paste that into the virtual space, then clear in a section of zeros, and then grab another section from the file and paste it in. What this is saying is, if the section alignment is less than the page size for the architecture, so 4K in this case, then it's going to want to do its copy paste on page boundaries, it sounds like, on page range granularity. So you actually have to make sure that the physical alignment in the file and the virtual alignment that you want match each other, because if they don't, then you can't just do this page granularity copying anymore. You'd have to do sub-page granularity copies, which it doesn't want to have to do. All right, so COFF relocations. Let's make a list of things we need to cover. Okay. Okay. Right, right. We're not doing relocations today, but there's all these different types of relocation systems for different architectures. Nobody who's ever worked on this has concluded that this is a good idea, but this is how it's done. COFF line numbers. So do I want to cover COFF line numbers? It says it's deprecated. I'm just going to put that there. Like that. The symbol table in this section is inherited from the traditional COFF format. It is distinct from the Microsoft Visual C++ debug information. A file can contain both the COFF symbol table and Visual C++ debug information, and the two are kept separate. Some Microsoft tools use the symbol table for limited but important purposes such as communicating COM data information to the linker. Section names and file names, as well as code and data symbols, are listed in the symbol table. The location of the symbol table is indicated in the COFF header. The symbol table is an array of records, each 18 bytes long. Alright, so this one is definitely one we want. COFF symbol table. Normally the section value field is a symbol table entry in a one base index into the second table. However, this field is a signed integer and can take negative values. Okay. More about the symbol table, auxiliary symbol records. The selection field of the section definition auxiliary format is applicable if the section is a comdat section. Okay, so we have a comdat flag. We don't have an example of it here. But that's okay. Okay. Wait, is this an auxiliary symbol? Yeah, these are more auxiliary symbols. This is all symbol table stuff. COFF string table. Here we go. Okay. So that actually is a more, it really goes with the COFF string table, or COFF symbol table. Attribute certificates can be associated with an image by adding an attribute certificate table. The attribute certificate table is composed of a set of contiguous quad-word aligned attribute certificate entries. Zero padding is inserted between the original end of the file and the beginning of the attribute certificate table to achieve this alignment. Each attribute certificate entry contains the following fields. Okay. Might want that. Delay load import tables. These tables were added to the image to support a uniform mechanism for applications to delay the loading of a DLL until the first call into that DLL. The layout of the table matches that of the traditional import tables that are described in section 6.41, the iData section. Special sections, okay. I'm going to sort of bookmark that part and go, does this have ID? Good. Typical COFF sections contain code or data that linkers and Microsoft Win32 loaders process without special knowledge of the section contents. The contents are relevant only to the application that is being linked or executed. However, some COFF sections have special meanings when found in object files or image files. Tools and loaders recognize these sections because they have special flags set in the section header, because special locations in the image optional header point to them, or because the section name itself indicates a special function of the section. Even if the section name itself does not indicate a special function of the section name is dictated by convention, so the authors of this specification can refer to a section name in all cases. The reserved sections and their attributes are described in the table below, followed by detailed descriptions of the section types that are persisted into executables and the section types that contain metadata for extensions. Right? Precompiled debug types, debug symbols, debug types. Linker options. Okay, So some of these contain stuff that I'm interested in. eData, iData. Let's take a look at, if I go to run and I run my DLL and I look at the sections, we have .text, .rdata, data, pdata, m4rdata, rdata, reloc. So I don't see any sign there of eData export tables. Symbol table is empty. DLL, right. Export table and import table are listed right here. Maybe that's where I want to start from. Yeah. Let's start from there. So I've got this stuff saved. Let's go look at the start from the top here. Data directory. The export table address and size. Okay. So what we're going to do is we're going to say in our dumper, we're particularly interested right now, because I'm interested in finding the export table. Parse export table. So what needs to happen here is we need to already be in the good state. We need to have data directories that are large enough to contain PE data directory data directory index, export table needs to be like that. And of course our data directories should be non-zero. Pretty sure that's redundant to this one though. Data directory count. Yeah, we set that if we've already got directories locked down. Okay, good. So data directories. Let's just shorten that down to dir. Data directories plus the export table index. There we go. So that's the one we want. And then that means we have the VOF and size for some kind of data. Let's look at how that data is defined now. eData section, image only. Boom. Here we go. The export data section, named eData, contains information about symbols that other images can access through dynamic linking. Exported symbols are generally found in DLLs, but DLLs can also import symbols. An overview of the general structure of the export section is described below. The tables described are usually contiguous in the file in the order shown, though this is not required. Only the export directory table and export address table are required to export symbols as ordinals. Export directory table. I think that's when we got an export address table. There must be things coming down. Okay. Export symbols as ordinals. An ordinal is an export that is accessed directly by its export address table index. Okay. So indexing instead of name lookups. The name pointer table, ordinal table, and export name table all exist to support the use of export names. Okay. A table with just one row, unlike the debug directory. This table indicates the locations and sizes of the other export tables. Okay. Okay, here we go. So this is everything related to export data. First thing we need is the export directory table. All right. We have our feet on the ground on this problem. Now we're filling in details. This feels like a good time for everyone to put on music. I don't play my music because I don't want to have to listen to copyright-free, copyright-safe music. I've got music that I like that is not copyright safe. I want to put that on. I recommend if you're hanging out and you need background tunes, you put on your own. That way we can all listen to whatever we want. I'm going to play video game remixes, this one. Okay. Very good. This is my new type, except it's all splatted out wrong, so let's unsplat it. This doesn't feel like a very useful way to write it down. If I did this. Yeah, that's helping a little. But not a lot. Okay, let's try a different approach. We're gonna go exit full screen mode, close one of my panels here, pop this here, pop that there. Okay, of course now I just went and lost the location in the, there we go. Any chance I'm gonna be able to hide this whole thing? Now it's gone. Never mind. Never mind. Okay. So we've got export flags. This is just going to be actually reserved 0. Okay. Timestamp. Major version major. Minor. The address of the ASCII string that contains the name of the DLL. These should be U16s. All right. So this is the name VOFF. So remember, RVA is their terminology for something that is relative to the base of the image in virtual space. My name for the same thing is the VOFF, virtual space offset. Ordinal base. Fine with me. The number of entries in the export address table. Export address count. The number of entries in the name pointer table. There's also a number of entries in the ordinal table. Okay, so we're talking about the ordinal count. The address of the export address table relative to the images. Okay, we got an RVA export address table. export address voff. The address of the export name pointer table. Okay. Name pointer voff. The address of the ordinal table relative to, okay, so that's the U32 ordinal voff. Okay. So if I got that right, I wish it could maintain the scroll location accurately between window width changes. That's annoying. Okay, if I've understood correctly, I think that the offset here should be giving me the offset to this. Let's just take a peek. Of course, this is giving me a V off, not an F off. So things start to get spicy right about here. In order to figure out where this goes, I'm going to need to go F off equals F off from V off, dir V off. And in order to do an F off from V off, we actually need all of the section data. Sec headers, sec count. Okay, right. The recommendation from chat is if you're not concerned with speed, then I would recommend loading the image. And what they mean, loading in quotes, what they mean is rearranging everything into the layout, into the virtual layout. So remember, we have the file layout, the way it's arranged on the file, and then there's the way it's arranged when it's loaded. And the recommendation is to do the rearrangement in memory. And the reason to do that would be because then it's much easier to handle the virtual offsets or the relative virtual addresses, the RVAs from Microsoft's terminology. Let me think about that. That's an interesting suggestion. I've done this stuff before and I never thought of doing that. It does sound nice and easy because then you don't have to do a mapping from V off to F off every time you want to load data that is pointed to with a V off, right? I'm about to do a F off from V off calculation just because this is a V off and I need it as an F off. And the suggestion would mean that I would just use the V off directly, and instead of using input data, I would have like a loaded or virtual data or like image data or loaded data, something like that, right? And then I would just do dir V off directly. It does sound easy. Do I care about the speed more than that? I do think it would be nice to actually have something that could rearrange stuff into the loaded space. Loading it wouldn't be too hard because we would just iterate the sections. We would start off by just iterating these sections here and creating that loaded version. such an interesting idea. I never thought of doing it that way. The thing is, when I've done stuff like this before, I did care about speed, so I didn't even have this as an option. So now I'm trying to evaluate if I care about speed in this case. I mean, the real answer is I kind of want to be able to do it both ways. I kind of want to see if I can get the loading to work. Like, I want to see what the loading looks like, and I want to see what this looks like, because I want to be able, I want to test out that I know how to arrange the loaded thing correctly. And I think that's probably pretty easy. And then using VOFs and getting useful, sane results would confirm that the loading was correct. I do care about speed in the sense that I do want to upgrade this over time. Right now I'm just dumping to learn the formats, like, and by learn it I don't mean just for myself, but learn it into the code. I want my code base to learn these formats. So I'm teaching my code base about these formats right now. And you know what? I think that coming back and doing speed later might be the right thing to do. Like, I could do another pass where I make a faster parse, but right now I'm learning the structure of the file. Let's do it your way. I've never done it that way before. That seems interesting. That's new for me. Let's take some steps back here. Wait. Okay, so something about this that's hard is I don't know if this applies to object files. On the other hand, this down here does not apply to object files. It might be that no situation where object files... Yeah, okay. So let's do this. Okay. Now, let's see. What is the, Nice. Okay. Yeah. Okay. Is this the one I need right here? Image size? We want to look at PE 32, PE 32 plus. Okay, right. So that'll give me the size I need. So we're going to allocate image size. So image size will get like this. Actually, p.h, pe 32 plus I know I have one. Yeah, here we go. 32 plus. It's 32 bits on both. So we grab our image size, and then what we're going to do is we loop over I also need to go and check here. Let's just start from, yeah, just starting from the beginning. What does get loaded? We need to figure out from scratch. All right, well, there's at least one thing I know I need to do. Let's just start with the part I know I need. We need to loop over all of our sections. And for each one, for each section, we need to copy from the file location to the virtual location. So memory copy buff plus sec voff image input data string plus section f off size, and the size there is going to be the smaller of the sections v off and the sections f off. So why is it the smaller of those two? If this is 0, it means that the size of this is bigger, right? This could be like a 0 section, and then we don't have anything to copy. We would have a certain size of the section in the image, but the size of the data in the file is empty because we're just going to let this be cleared to 0. If this is smaller than this, I don't know exactly how that would be relevant, but you wouldn't be able to fit all of this in here anyway. So whichever one is smaller, that's how much copying there actually is to do. Now, some of those arrangements might be invalid, but but I don't care about that right now. So that gets me at least all of the section data is loaded. What I don't know is what I don't know if there's other stuff like the headers that I need to copy over to. Let me just look for the word load everywhere and see if anything pops up that is useful. Location of an item within the file itself before being processed by the linker, in the case of object files, or the loader, in case of image files. This is a position within the file as stored on disk. Yep. The linker produces an image file, which turns input by the loader, term object file, yeah. In an image file, this is the address of an item after it is loaded into memory, with the base address of the image file subtracted from it. Yep. The basic unit of code or data within the PE or COFF file, for example, all code in an object file can be combined within a single section. Each function can occupy its own section. With more sections, there is more file overhead, but the linker is able to link in code more selectively. A section is similar to a segment in Intel 8086 architecture. All the raw data in a section must be loaded contiguously. Yeah. In addition, an image file can contain a number of sections such as TLS or reloc, which have special purposes. Sure. The file does not contain base relocations and must therefore be loaded at its preferred base address. If the base address is not available, the loader reports an error. The default behavior of the linker is to strip base relocations from executable files. Okay. If the image is on, I'm curious. When I look at my run image file characteristics, so this should be executable image, large address aware. It does not show relocation stripped, interestingly. Okay, something else I could do here is I could look at our sections and make a little map. So we have one from there. Yeah, okay, so this makes sense. It's all laid out in order here. This is going to go up by 126 kilobytes. So, just so we're clear, here's 4 bits, 8 bits, 12. So, 12 is 2 to the power of 10. Same thing as 1 bit shifted 10 times. That is 1 kilobyte. So 2 to the 12, which is 1 bit shifted by 12, is equal to 2 to the power of 2 times 1 kilobyte, or 4 kilobytes, right? Which, of course, 1 bit shifted by 12 is 1000, right? So each of these is 4 kilobytes. So this here is 32 times 4, 128 kilobytes, which is what we'd expect, right? 128 kilobytes. $58 kilobytes. That's gonna round up to 64 kilobytes. So that would be like 64 divided by 4 is 16. So that'll be a 1 right there. Oh, but it's yeah. I'm being too aggressive. We don't actually need the full 4K there, I guess. Right. Really, this could round it up to 60 kilobytes. That rounds up to 128 kilobytes. That rounds up to 60 kilobytes. Right, so these are just laid out like that. The point is, none of these all fit together perfectly to create that image. What's going on in those first 4K? Well, the header's size is 1K exactly, interestingly enough. How much does header's size cover? That's what I want to see. Optional headers. Oh, this search thing is, like, not very good. Optional header. Okay. The combined size of an MS-DOS stub, PE header, and section headers rounded up to a multiple of file alignment. So I bet you we can copy all of that into the image, as long as this is less than the image base. No, not the image base. The smallest VOF of a section, basically. What I don't see is any exact specification of what gets loaded in, but I think that, if I remember correctly, all of this has to get loaded in so that the parsers can still work on the image. So I'm gonna say let's do that as well. To create the loaded version, we load the sections. This is allocate the buffer. Init loaded data. Headers. Copying into the buffer from the input data.string. The header size. Okay, now the idea is if I've done that, now I can come in here and I can go, what is the data directory looking at? The data directory is looking at PE. We just set this up. Wait, we want to get the export table, export directory table. That should be the export directory table loaded data.string plus dir voff. But that's if dir voff plus dir size is less than or equal to loaded data.size, right? And then set this up for a debugger breakpoint. Whoops, somehow I didn't get the breakpoint in there before it started running. Whoops. All right, export directory. This doesn't look right. Hold on. Yeah, that's test.exe. There's 16 of these. Yeah. Now, hold on, though. I thought this looked right. Unless it's not zero base. That might be a thing. Let's take a look at that in a sec. Yeah, this is saying export table. Right. Okay. Right. So if dir voff does not equal 0, I guess, or vsize, maybe we could check the size does not equal 0. So that's just my bad. This doesn't work because I don't have any exports in the test.exe. I have exports in Mr. Forth base DLL. Let's check that one. There we go. Now we've got exports. Now our export directory looks valid. That's reserved. Timestamp is uint max, which means it's nothing. It's just a fill-in, major version, minor version. I haven't said anything like that. Name voff is interesting. That's probably pointing to something real. Ordinal base is 1. That's what we expect. We have 10 exported addresses, 10 ordinals, and we have offsets for each of those. Okay, that looks right. Okay, cool. All right. So now it feels like the loading has worked correctly. Let's switch over to testing the DLL. Okay, so there we go. If we find an export table, we'll continue from there to extracting everything else that the export table has to offer. So let's see. Once we have an export table, then what do you do? Well, there are Start with this one. I guess export. I don't exactly know what this is referring to yet, but let's try this. Straight from a C string. Okay. So we want to take the loaded data.string. And we want to add in the export directory name voff. I bet you that's a C string. Let's take a look. Okay, so that's the name of the DLL, which is ourselves. Which is fine, I guess. Something like this. I'm not really sure. It's a little confusing why this thing contains its own name. Maybe in case it gets renamed and we need to figure out what's wonky. I don't know. All right, so we got the name. What else is interesting? Give me the right ones here. There we go. So we want that, and now we're ready. Okay. Had to get all my windows arranged in the right order for Alt Tab. So ordinal base, starting ordinal number. Yeah, so we know about that. That's set to 1. Address table entries, the number of entries in the export address table. Okay, so that's this. The export address table contains the address of export. Let me turn my music off for a minute so I can read. The export address table contains the address of exported entry points and exported data and absolutes. An ordinal number is used as an index into the export address table. Each entry in the export address table is a field that uses one of 2 formats in the following table. Each entry in the export address table is a field. Okay, if the address specified is not within the export section, as defined by the address and length that are indicated in the optional header, the field is an export RVA, which is an actual address in coder data. Otherwise, the field is a forwarder RVA, which names a symbol in another DLL. Okay. So these, it's like a union. I get it. So each of these is a 32-bit offset. Like this, right? But there's like, it's nothing. Like there's nothing special or unique about it. It's just a bunch of U32s. So what we want is U32 export addresses equals U32 we get when we take loaded data.string plus export directory export address voff and that is only going to be valid if we need to see if the man, it's huge. It's a huge amount there. How do I want to shorten these names? Okay. Okay, music, you can come back. All right, so there are 10 exports. And if I look at those as hexes, they look like this. Okay. So that seems good. Now, what was the whole deal about there being two different types? Well, if I understand correctly, each of them is basically a VOF. And if it's within the range given by the directory, then it's an ASCII string. And if it's outside of the directory, so basically if it's one of these, it's saying, hey, I actually don't contain the symbol. The symbol that you're looking for from me is actually contained somewhere else. And this is saying, hey, it's outside of that range. So instead of being a string that forwards this to another DLL, then it's the actual address of the symbol, like the pointer to the beginning of a function or the pointer to a global variable. So in order to print these, we're going to need not going to need that. We're going to need like export range min and max. So there we go. Then if we have an export directory, export range max, there we go. And now I should be able to print these. So exports. Exports. I'm going to just rename export directory to exports. For now. Exports PE export address count. Export VOFs. Export VOF equals export VOFs I. So this is, of course, if export VOFs does not equal 0. We have to have some kind of check there. So we grab the export VOF, and we have two cases. If this is a forwarder, we will know because export range min will be less than or equal to export voff, and export voff will be less than export range max, right? And so then we go, okay, if it's a forwarder, we're going to print it one way. If it's not a forwarder, we're going to print it another way. So this is going to be something like export %u equals, and then this is a string, new line, this is I, this is exports. Exports has an ordinal base, we'll add that in. That reminds me, sections are actually one based. Okay. And then we need the string. And we get that from loaded data dot string plus export voff and then we actually want a safety version of that we don't have yet, but there we go. In other words, and otherwise, we have export %u equals ox% x. And that's again like this, except now we're just looking at export voff itself. And there they are. But that's not everything we want. That's just the offsets. We actually need more. So, going back up here, export voffs gave us some of the information we want, but there's more. All right, I've been streaming for a couple hours. I'm gonna take a quick break, not very long, but I'm just gonna go for a minute to get myself some something to snack on, because I'm a little snacky, and I will be right back. All right. It's an array of RVAs into the export name table. The pointers are 32-bit each and are relative to the image base. The pointers are ordered lexically to allow binary searches. (16-bit) unbiased indexes into the export address table. Ordinals are biased by the ordinal base field of the export directory table. In other words, the ordinal base must be subtracted from the ordinals to obtain true indexes into the... So it's unbiased indexes that are biased by the ordinal base. Blah, 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 blah. So much blah, 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 blah in this documentation all the time. Just blah, 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 all the time. So confusing. JVS Tech, yeah. RVAs, I've dealt with this stuff before, so I have my own naming scheme even for them. I call them VOFs, virtual offs. And the reason I do that, the reason I rename them, is because ultimately part of the goal is to abstract this and ELF. And so I just end up making my own naming schemes and mapping their stuff to my stuff. So what they call a relative virtual address, I call it a virtual offset. But yeah. And what we're doing right now to deal with that is I'm just like creating a buffer here. This was a suggestion from Recyrillic. I've been avoiding saying your username because I'm not sure what it is. Recyrillic. Maybe if I make this text bigger, I'll be clearer. But they suggested that what I do is load the image, basically take the file and rearrange it into its loaded format so that I can just use the VOFs or the RVAs directly on that, which is pretty good. So what I'm doing here is I'm trying to figure out what the mapping is between these things. When the export name pointer table is searched and a matching string is found at position I, the algorithm for finding the symbols RVA and bias ordinal is search export name table name gives you an I, ordinal equals export ordinal table I, RVA equals ordinal, bias ordinal equals ordinal plus ordinal base. Oh wait, so ordinal base field on, in other words, the ordinal base must be subtracted from the ordinals to obtain true. Okay, so these are unbiased. That's so confusing. These are unbiased, as in the zero, a zero in this is a zero index into the address table. I get it. So let me map this out. Name takes me to an index. We're going to have to do some information flow mapping here. So a name takes me to an index. And that is via the name table. And then the index takes me to an ordinal. We'll call this an unbiased ordinal. And that is via the ordinal table. The ordinal takes me, the unbiased ordinal takes me to a VOF, and that is by the VOF table. And of course, the unbiased ordinal combined with the base ordinal can give us the ordinal, which we don't care about, but that's what they're trying to tell me, is that I can combine these two things to get the bias ordinal. Okay. So this matters only if someone gives me a bias ordinal in the first place, because then we can reverse that, because right, you just, like, there's a way to get the unbiased ordinal from that, and then you can do unbiased ordinal. Yeah. Okay, let's try this out. So how do I want to print this now is the question. I have a list of VOFs here. Essentially, let's just print the raw thing, and then maybe I will structure it more clearly as I go. So the raw thing, these are name pointers. So here's our name. Here's our export VOFs. Here's the name. Now let's get ourselves the export names. This is going to be export address count? No, ordinal count. And the names VOF is going to be the exports name pointer VOF. And then we want the after names VOF to be the names VOF plus the names count times the size of U32. If the after names VOF is safely inside the range, then our export names is that. Okay. Does that look logical? Yeah, those look like the exports from my DLL. All right, so let's see. Those names look reasonable to me. And then I bet if we look at the ordinals, it's just going to be like 0 equals 0, 1 equals 1, blah, 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 right? Because in this case, I think that it didn't have any trouble lining up. It's like there's an extra layer of indirection in the ordinals thing, I bet. All right, export names. Export ordinals. I think those will be U16s, actually. Is an array of 16-bit unbiased indexes. Right. Ordinals count. Ordinals count times size of U16. Ordinals voff is inside the export range. Then export ordinals equals loaded data plus ordinals voff. Export ordinals, ordinal count, U16, export ordinal, ordinals, ordinal, ordinal voff. It's right here. How are they spelled different? Original. I see the misspelling. Okay. Okay, yeah, so here's what's happening. It's really confusing because these are all equal to each other, so it's just an identity mapping in this case. I guess this doesn't necessarily have to be true, but what's happening is if you have a name, then the way you look up the offset for that is you search in this table. This is sorted by, this is sorted alphabetically, basically, lexicographically. So you'll be able to binary search this for the name you're looking for, find it, boom, and then you go, okay, this array is parallel to this one. They have the exact same length. So if I have a 5 here, I plug in the 5 here, and I find out what ordinal I'm looking for. That ordinal then indexes into this. Now, this ordinal is unbiased, so this 5 does not go to this 5. This 5 goes to this 6. These are the biased indices. So what we could do to indicate that idea is we go plus %u, right, like this. And then we're just going exports ordinal base, right, like that. And then we got this. So this contains 0, which refers to this. Right, position slot 0 in this array. Okay, so now the question is this the correct way to print this data structure? I think a better way to print this would be to iterate the export names, and for each of the exports that we see there, we would, this is parallel, look up the ordinal here and grab the voff and put them all down at once. So the final version of printing the exports would be like this. If export voffs, hold on, let's do one other thing here. We try to get all of them, and then at the end we're going to say b32 good exports equals 0. If we go this far, if export voffs does not equal 0 and export names does not equal 0 and export ordinals does not equal 0, then good exports equals 1. And so if we want to print our exports, if good exports, then we do a loop over the names like this. And we say, get us our name voff and our ordinal. Get us our name. Then get us our actual export, which is going to be based on taking the export ordinal. This would be the unbiased ordinal. That gives us an export voff. We check if it's a forwarder. And then finally we go export something like this. Exports ordinal base plus ordinal export unbiased ordinal. So there's our biased ordinal goes there. Name goes there. Forward goes there. Export name forward string. And then this one is very similar. It's just instead of having a forward, we have a voff. And that's the export voff. So now our exports, oh, and then we still are printing all the other crap. Get rid of all of this. Nice. Cool. Cool. All right, let's mark that as done. Cool. So I guess another thing to do here is to look at import symbols. That's kind of nice and parallel to the idea of export symbols. Let me also, before I go on, let me just document real quick a little bit about how the tables work here. Okay. Okay, there's everything about export data that I want to include. Let's look at... Wait, what is this and how is this different? So something interesting here is that if something doesn't have a name, it doesn't have to show up in this list, and then it could still show up in the export address table, which is without a name, right? It could be linked only by ordinal according to all of this. And then my dumper doesn't actually know about that. I'm trying to think of what the best way to deal with that is. I could say let's loop over the exports themselves because those are absolute. And then at each index, I would have to scan the ordinal table for a match, and if it has one, then that's the name. But if it doesn't have one, then it's just not assigned a name. Okay, I know what I can do. All right, so we're looking at the VOF for, each VOF that we grabbed out of the file. We check if it's a forwarder. If it's a forwarder, we do one thing. If it's not a forwarder, we do the other thing. Here we C-string that. Otherwise, we save the VOF itself. And then we do another loop, this time over the ordinal count. And now we're doing something like this, where we grab the name in the ordinal. And what we're going to do is say, get the export name. And go back into the export sim again, this time using the unbiased ordinal. That way, we can do 2 linear loops to build a data structure that fully represents the table, the expanded table. And then in a final single linear loop, we just go export sim count. Export sim equals export sims plus I. Now, if the export sim voff or forward.size does not equal 0, then what we do is we print if the export sim name.size does not equal 0, then we take ordinal base plus I as the ordinal. So those will come out in order. The name, and then the forward string. Something like that, maybe. And if you don't have a name, then we just skip that part. And instead of forwards, we have OX%X's voff and voff without the name. Okay. So now these will always come out in the original correct order, and anything that doesn't have a name won't show up. As a final thing, since I'm still actually working on exports here, now that I've gone through it and looked at these, let's rename these to be a little bit more accurate. So name voff, this is more like the binary name voff. Ordinal base seems fine. Export address count seems wrong. Let's just call that the export count. Export address voff seems wrong. Let's just call that the export voff. Okay, I'm going to fix that here. So an export and an export count. I'll also rename this from name pointer just down to name. So I don't see any reason why I should make it more complicated than that. Okay. Oh boy. Where does that leave us? I think we can check that into okay. Now let's take a look at those imports. The image files that all image files that import symbols, including virtually all executable files, have an iData section. A typical file layout for the import information follows directory table, null directory entry, DLL1 import lookup table, DLL2 import lookup table, DLL3 lookup hint name table. This is weird and not very clarifying of anything. The import information begins with the import directory table, which describes the remainder of the import information. The import directory table contains address information that is used to resolve fix-up references to the entry points within a DLL image. The import directory table consists of an array of import directory entries, one entry for each DLL to which the image refers. The last directory entry is empty, filled with null values, which indicates the end of the directory table. Each import directory entry has the following format. Kernel number. Okay. All right. Let's try to encode this. It looks like we have 4 32-bit integers. I'm going to try to just see if we can do it this way. import lookup table voff timestamp forwarder chain, the index of the first forwarder reference. First forwarder index, something like that. We're not sure yet. Name voff, the address of an ASCII string that contains the name of the DLL. This address is relative to the image base. Yep. Import address table voff, the RVA of the import address table. All right. I think I will take another short 5-minute break and we'll pick it up from here. We're going to try to get the import table working. I'm not sure if I have, I think I have something with an import table in it. Let me see if Mr. Fourth DLL actually has one. Yeah, it does. Okay, so this will work. We'll pick up from there trying to look at this import table. All right. I see. These null directories. So this is the directory table plus a null directory entry. So we're going to scan these until we find a null directory entry. Parse import table. Import directory table. Okay, so for now, I think we need to figure out how many of these there are, just to get started. And so what we're going to do is start a loop. We need to also know what the maximum count is. So that's going to be dir voff divided by the size of PE import directory table. So we can't have more than that many. And we're also going to try to find out if there are even less than that. So for each import directory, if import dir import lookup table voff equals 0, then we break, and wherever we stop, we get import dir count equals import dir minus import dirs, right? That gives us our final count. Let's just see that much happen in the debugger. Nice. So there's 1, 2, 3, 4, 5, and then 0. So we found 5. So import dirs, if I look at 6 of these, the last one is null, and the previous ones are all good to go. Okay, cool. Now, what do we want to do from there? It looks like each of these comes with more information. So I suppose we want to figure out this is where it starts to get a little complicated, because we kind of want to print this loop here. We want to print each of these, but these also contain sort of more concepts within them. So we don't want to start having some of the parse code living down in the dump part. We don't want to have to make the parse part too complicated. So we might need to start building an intermediate data structure that contains what we found here along the way. We'll see. Let's go and just look at the data structures for these. So look up table voff. What is that? An import lookup table is an array of 32-bit numbers for PE32 or 64-bit numbers. Each entry uses the bit field format that is described in the following table. In this format, bit 31 is the most significant bit. The last entry is set to 0 to indicate the end of the table. Okay. Yeah, I think I'm going to just start a helper right now. This is going to be easier if we do it as an intermediate data structure. Import table. I'm not sure exactly what I want to call it. We'll build these one at a time. Address table voff. So this looks like it's a runtime feature. It's initially identical to this. But once the image is quote-unquote bound, what I think they mean is once it is loaded and linked up with other things, this is the version that tells us how to redirect or something like that, the imports to existing addresses, maybe? So let's see, the high bit gets used, and then either 0 through 15 or 0 through 30. So why did you guys make it the 64 bits in PE32 plus, but still only use 32 of the bits and just make it all this complicated stuff? I wish you wouldn't have done that. Okay. All right, for now what we're going to do is we're going to just go like this. All right. All right, so with each of these, we're going to grab a new import table off of our arena. We're going to queue that up. Import table first, last import table. Import table count is going to go up by 1, and then our import table is going to grab some of its stuff straight from this import directory. Right, those were directly copied. Now the import table name comes from this like unsafe C string business that we're doing. Loaded data string plus import dir name voff. Now finally the import table lookup table is going to be one of these two things. If PE32 does not equal 0, we're in this mode. Otherwise, we're in this mode. And either way, it's just loaded data.string plus import dir lookup table voff. And of course, these don't come with counts. So let's add one. So we're going to take the start of this and the something max. I can't remember what it's called, and subtract them divided by the size of a U32. What is that thing called? Import range max. Alright, so that's how large it can possibly be. And now okay. Cool. Okay. So I think that should do the trick. Except this needs to be a 64. Okay. So we have each import table. Kind of, right? Let's just go and print what we have so far so we can get a handle on how far we've gotten. Imports. All right, so what do we have? We want to have name equals like that. Table name. We'll throw in the nonsense here. This isn't going to work. Let's do this. Imports. Well, this will work. It's just kind of annoying. Percent %u first forwarder index equals percent %u. Timestamp table first forwarder index. Okay. Cool. Okay. So this makes sense, right? We're seeing what makes sense here. These names make sense. So all we really need to do is figure out what these should actually look like, right? Now, we know we're in PE32 plus mode. So I think I'm kind of debating here, but I feel like the easiest thing to do is just going to be to use some macros here. Import lookup PE32 is ordinal. It's going to be like this. 1, 0, 131, right? 32 plus is ordinal is 63. Now they say the ordinal is 16 bits. So that's the ordinal. And that's true either way. And this one is 1, 2, 3, 4, just the 31 bits like that. And so all we have to do is if PE import lookup PE32 is ordinal, lookup ordinal equals PE import lookup get ordinal lookup. Name voff equals get name voff. Okay, if we have a name voff, okay, this is strange. So these aren't just name voffs, they're like hint voffs. And a hint looks like this. It's got 2 bytes, looks like this. An ASCII string that contains the name to import. This is the string that must be matched to the public name of the DLL. The string is case sensitive and terminated by a null byte. Okay, so this is the hint ordinal. Basically, it's saying it tries this first because it thinks it knows where the symbol is going to be, so it can look it up directly. And if that fails, it'll use the name in a binary search. And then possibly some padding, because this is a variable length C string. Okay. So a hint looks like this. Hint ordinal is what we get if hint voff plus 2 is less than or equal to loaded data dot size, then the hint ordinal is what we get when we dereference loaded data dot string plus hint voff as a 16-bit integer, and then hint, here's the name, here's the and this is where we want a safety version. That's just going to be loaded data dot string plus hint voff plus 2. And I don't know. It's debatable. Is this crossing over into parsing to do it this way? Because this is the dumping code. Is this crossing over into parsing? Kind of feels like it with the C string happening here. We might want to define the sum type as a data structure we can parse out and store. Okay. That's not quite looking right. It's kind of weird that it's every other one that's messed up. Right? Ah, here's why. Definitely feels like we should parse that ahead of time. But there we go. So there's everything getting imported. Cool. All right. So I think that's good. Like I think let's try to fix the thing where the parsing is happening in the dumping a little bit too much there. Why don't we replace the union of arrays there with PD import lookup or import symbol or something like that, right? And then this will be This will be sitting here saying something like, okay, I want, I have an ordinal, I have a name, and I have a question that's like, am I... Well, I don't think I need anything else. If the name is null, that's this case. If the name is non-null, that's this case. Done, right? That's really all that we're doing here. They're encoding it tightly so that it's right in this array of if there's ordinals, but then we're finding out that every single one of them is actually jumping out to this sort of thing anyways. So, yeah, let's just do pe dump import symbol sims, right? That's going to break what we've got for a minute. But what we're going to do is we're going to go, okay, now that we've got a lookup table and a max count, let's figure out our actual count. Let's allocate some import symbols onto our arena. And then let's do a loop where each symbol can get filled. So this will end up being our count. And this will end up being our sims. Good. So we can pull these two out. So we look at each of these and we go, is this an ordinal? When we look at lookup table J, lookup table J. If it's an ordinal, then we do sims j dot ordinal equals get the ordinal. And we're done. Otherwise, we do get the hint v off. You know, all of this would be easier if I could do it something like this. Lookup table, lookup stride is ordinal mask bit position, something like that, right? And then what we're going to do is just try to get down to one parse loop with these things being like this. Actually, this is even better. That is not dependent either. So all we're doing is lookup stride needs to change, and is ordinal bit position needs to change. It's even better. It's even better because it's the high bit is going to be in the first byte. Either way, we'll just read one byte and look at its high bit. Let me think, let me think, let me think. Okay. Then putter plus equals, oh yeah, let's pull J out like this. That'll give us our final count instead of the pointer, so we don't have to do a divide. This is going to increment by the lookup stride. When we get to the end, the sim count will just be J. And then we allocate our symbols. And again, we're going to have a U8 putter going along. So we got a lookup pointer going along, and then now the question is, can we do is ordinal in the easy way? I think we can. We go lookup, we go putter, dereference, and OX80 does not equal 0, right? So the point is, we'd look at the first byte, we look at its high bit. Is ordinal. Is not ordinal. So if it is an ordinal, we go sims j ordinal equals, and now what we have to do is we look up right? So that gives us the low 2 bits, and the ordinal is just a U16. If it's not an ordinal, then this is the hint that you get when you do looking at a hint v off, lookup stride -4, and OX7F 1, 2, 3, 4 bytes. Now we've got our hint v off. And what do we do with a hint v off? We want to extract a hint ordinal and a name, and those go into the J symbol. Hint ordinal Okay. All right, now for printing, all we have to do is we go, forget the bit where we look at the PE32 versus PE32 plus. We just loop the symbols. We grab an import symbol, we go sims plus I. If the name is empty, then it's this case. We just print the ordinal as an ordinal only. It's the only way to link. If the name is not empty, then we print this case. Sim name, sim ordinal. Okay, so that doesn't quite work. So probably something wrong with my logic in here. Oh, right. Right. I got my big endian, little endian flipped around there. Let's try that. There we go. Nice. Nice. Okay, so that's looking better. I think put the exports there. Yeah, okay. I think we can call that a step. Cool. So maybe we keep looking at these data directories here. Resource table is empty. Exception table. Certificate table is empty. Base relocation table. Debug. Architecture is empty. TLS table. Load config table. IAT. Okay, so these are the ones we have here. Exception table is probably going to be fairly intricate. So I'm thinking whether or not this is a good place to end for the day. I think the correct next things to do is to just keep plugging away at this stuff here. At some point, I need to figure out how I'm going to incorporate a disassembler, and I'm not sure, right now might not be the right time for us to write our own disassembler. That's definitely on the list of projects to get to some days, to write our own disassembler. But maybe we'll just put one in for this for now. These are just data sections we would drop in hard. We would need a relocation, or raw, I should say. We drop them in hard. This is a relocation. We would need to learn how to parse that at some point. So there's still a lot to do just on dumping these. And let's also, while we're at it, let's make sure, as a conclusion for the day, that things like this are still working. Now that's crashing now. All right, cool. So let's make that our final thing. Let's figure out why that started crashing and try to address that, and then we can be done for the day. It's probably just like an old dereference somewhere where it works only if the data is present. What do we got? So dir voff, dir is null. If good, dir, right? We don't necessarily get a dir. Okay, so 364. If dir does not equal 0, that covers the rest of the import table. Yeah, so this already had a check. Really, we want to see if import dir does not equal 0. Import dir does not equal 0. There we go. Cool. All right. That feels like a good stopping spot for me for today. I'm going to continue to be working on this for some time. There are other stuff that I'll stop to do along the way, like, you know, we're getting to the point where it's like probably it would be good if I could print tables. Like, I am not printing a lot of tables right now. And, yeah, I'm doing these as like structs, but formatting out ASCII tables might be a good side project for all of this. Taking a look at ELF side by side with this eventually once this has gotten pretty built out, but maybe I want to get started on ELF sooner rather than later too, to sort of see where they're parallel and where they're not earlier. I don't know. Also, like, separating this out right now, I'm just writing a dumper, but over time I want to take the knowledge that's in the dumper and graduate it up into more and more advanced reusable analysis stuff, and eventually turn this into a full-on visualizer for these kinds of things. So like when we, right now, when we look at this, we see we've got imports and exports. But as this continues, we might start wanting to do things like not just seeing these as tables, but actually start like being able to drop a file into a visual explorer and put it side by side with another file and see how the exports of one and the imports of another line up and stuff like that. This could get arbitrarily fancy, and of course I want that visualizer to understand not only this format but the ELF format and the debug formats for Windows and Linux as well. So there's quite a lot. There's also making a library out of it so it can be used for things other than a visualizer, so it can be used for all kinds of stuff. Ultimately, this all ends up with things like, I don't know if you all remember this. This is from one of my YouTube videos. But profiling by Spall autohooks has this problem right now where when we use this, if you recall, what autohooks does is it inserts your profile begin, profile end functions into all of the functions. So when you compile, it goes, I understand that you are trying to instrument your code so that you can see all the function calls, but it doesn't hand you the function name. when it calls you at the begin. It only hands you the virtual address of the function. And so that leaves you to decide how you're going to turn that virtual address into something. So right now it just marks them all as function. And I want to be able to, using debug information / information in a binary, do as good a job as possible of mapping those addresses to names with a tool like this. That's the kind of stuff we could start doing. We could also start looking at how things link up to each other dynamically, planning that out. There's lots of more advanced native layer control stuff that I think is possible on the other side of really getting a handle on this. So lots of more stuff is coming on this project for a while. I'll also probably make some videos about the progress now and then and explaining how these things work. But that's it for today. If you like the sound of this project, you'd like to see me be able to keep doing it for a while, because it will take some time. I do need some support. I need money to be able to keep doing this. So if you like what I'm doing and you want to see me make this into libraries and informational videos and visualization tools and stuff, consider supporting me or becoming a member of MrForth.com, of the Mr. Forth Lab. This is what funds me to keep going. I'm depending on everyone who's watching to consider and see if they can do that for me. But with that, I'll be signing off for today, and I'll see y'all around later. Bye-bye.